Hi, this is Andrea Hendricks. The topic of this video is how to solve linear systems using matrices. A matrix may be some new terminology for some of you, but it's a quite simple idea. A matrix is just simply a rectangular array of numbers enclosed by brackets, like something like this, where we have a bracket 2, 4, 3, -7, brackets 1, 0, 0, 1, 4, -2, 1, 3, 6, 8, -5, 7, 0, 1, 9, -1. Okay, you're thinking, what do those numbers mean? I promise I'm going to bring them back into solving systems. But the way we denote the size of a matrix is we say it's m by n, where m is the number of rows and n is the number of columns. So for this first system, or matrix rather, we have, 2 rows and 2 columns. So this would be called a 2 by 2 matrix. The same thing goes for the second one. We have a 2 by 2 matrix. Now notice the third matrix we have is how many rows? 3 rows by 4 columns. Okay, and identifying the size is going to be important when we get to the calculator. So it's always rows by columns. And each number in the matrix is an entry, and so we denote it by its position in the matrix, like the 3, for instance, is on the second row, first column. Okay. Now, why do we use matrices, or why even talk about those when we're thinking about a system of linear equations? Well, when solving a system of linear equations by elimination, do you realize that it's the coefficients that determine what we do? The x, y, and z are just there kind of taking the brunt of everything that's going on with the coefficients, but they really don't add what we do to solve the system. So let me show you, for instance, here. If I have this system, 3x minus 2y plus 5z is equal to 31, and x plus 3y minus 3z is equal to -12, -2x minus 5y plus 3z is equal to 11. We've already talked about how to solve this system, but let's just go through it again so you can kind of get the feel for what I'm talking about. Remember that the idea is to eliminate a variable from the system so that we come up with 2 equations with 2 unknowns. And if we just number these, equation 1, equation 2, and equation 3, and the first thing that we want to do is to add equations 2 and 3. And we add these 2 equations together, we're going to come up with what? X minus 2x is really a -x minus 2y. The 3z's add to 0, and that would be equal to -1. Okay? Then we can also eliminate the z from another equation. To eliminate z from another equation, we have to use 2 of these and try to use the process of elimination to get the coefficients opposites, right? So let's use the 1 and 3 now. If we use 1 and 3 to do 3x minus 2y plus 5z equals 31, -2x minus 5y plus 3z is equal to 11. And let me step back for just a minute before I do that, and just kind of keep track of the steps that we did. We actually added our row 2, or equation 2, plus row 3 to come up with this new equation, right? So now what we can do is we can multiply row 1 if we think about trying to eliminate the z's, 5z and 3z. The opposite or common number that they both go into is 15, right? So we would need to have a positive 15 and a negative 15. And in fact, instead of using 1 and 3, let's use 1 and 2 because the sign's already opposite and we don't have to deal with that. So if we want to get between 5 and -3 of 15, we need to get a positive 15 and a negative 15. So what we can do is multiply the first equation by 3, right? So if I do 3 times the first equation, so if we do 3 times row 1, I get what? 9x minus 6y plus 15z is equal to 3 times that would be 93. And then if we multiply the second equation by 5, we would get 5x plus 15y minus 15z is equal to -60. And so now we can add them together. When we add them together, we get 14x plus, what is that, 9y is equal to 33. Okay, so this was really 3 times row 1 plus 5 times row 2 is how we got this equation. So we have 14x plus 9y is equal to 33. But you understand what's going on. The only thing I'm really doing are playing around with these numbers to make them come up with what I need. That is, where I need opposites or things like that. Now, how would we solve this system? Right, we could eliminate the x, because a common number between -1 and 14 would be 14. We already have a positive 14, so to get a negative 14 in the first equation, we can multiply it through by 14. So that would give us negative 14x minus 28y is equal to negative 14. The second equation stays the same. And upon adding, we would get, what is that, negative 19y is equal to 19. And then dividing by negative 19, we get y to be negative 1. Okay. So if I know y, what would I need to do now? Yeah, I can find x. So to find x, we would have to plug into one of these equations. We have negative x minus 2 times y. Y is negative 1. And that's equal to negative 1. So we really get a negative x plus 2 equals negative 1. So negative x is equal to negative 3, so therefore x is equal to 3. So the last thing we need to do is find z. So we plug into the first equation, if you like, 3 times 3, because the value of x, minus 2 times y, which is negative 1, plus 5z is equal to 31. So we get 9 plus 2 plus 5z is equal to 31. Well, that's 11 plus 5z equals 31. So if we subtract 11 from both sides, we would get 5z is equal to 20. So z would be equal to 4. So our solution is the triple 3, negative 1, 4. Okay. So we did all of that with the variables just kind of being a placeholder for us, so we kept our like terms lined up. Well, we can actually use a system or a matrix to solve this system, and let me show you how we would do that. So since it's the numbers that really make a difference, we can just use a system, or I keep saying that, I'm sorry, a matrix, and we actually form what's called an augmented matrix. And the augmented matrix picks off all of the coefficients of the variables plus what the right-hand side of the equation is. So for that particular system, let me write it here again. We had what? 3x minus 2y plus 5z is equal to 31. X plus 3y minus 3z is equal to negative 12. And negative 2x minus 5y plus 3z is equal to 11. So our augmented matrix is going to be just to look at the numerical coefficients and what the right-hand side is. So if we think about the coefficients are 3, negative 2, 5, and then we can draw an imaginary line here just to understand that the right-hand side is 31. Then we have 1, 3, negative 3, and negative 12. Negative 2, negative 5, 3, and 11. So our goal is to use this matrix of numbers to come up with the solution for the system. Well, if you remember what our solution was x was equal to 3, y is equal to negative 1, and z is equal to 4. Well, if we think about what the augmented matrix of that would be, think about it like this. Our x coefficient is a 1, right? This is really x plus 0y plus 0z is equal to 3. So we'd have a 1, 0, 0, 3. Y equals 1 is really 0x minus y. I'm sorry, not minus y. Plus y. I was looking at my negative 1 there. 0x plus y plus 0z is equal to negative 1. And for z equal 4, that's the same thing as 0x plus 0y plus z is equal to 4. And so understand where the variable has been eliminated, it really has a coefficient of 0, right? And so that augmented matrix is 1, 0, 0, 3, 0, 1, 0, negative 1, 0, 0, 1, 4. So our goal is to perform operations that would get us to this type of matrix. Because if on the left-hand side of this imaginary line, if you will, we have what is called the identity matrix, then we know the solutions are in the right-hand side. Well, to go from one matrix to the other, we can do what's called row transformations. And the things that are legitimate are the things that we did when we were solving it by hand. That is, you can multiply a row by a number. You can add rows together, or you can add multiples of rows, and you can also swap rows. Now, lucky for you, we're not going to go through and do this by hand. If you're interested in how to do this, you can certainly do it in the book. We're going to just rely on the calculator to do that for us, but you can kind of think about what you would have to do. I mean, you know how we started out by adding equations 1 and 2, not equations 1 and 2, equations 2 and 3 to eliminate the z's? Well, you could think about doing that. If I added those two and then replaced the third row with that result, that would be one way that I could start. So just knowing what those coefficients are allows me to come up with a system without really ever being involved with those x, y's, and z's. The columns take into account the location of that constant term or that coefficient. So you're not going to have to do these by hand. In fact, doing them by hand is completely optional in this course, and I know you're probably at the point where you're thinking, I don't want to have to do one more thing. And so our goal is to get this into what we call reduced row echelon form. Okay? And that is an augmented matrix that looks like this. And you're going to use your calculator to do it. So you're going to enter the matrix, and I actually have a calculator video that shows you how to do that. And there is a command that is called ref. That will put the matrix in the form we need. The two things that you need to be mindful of is that whenever you're solving, you get something like 1, 0, 0, 3, and 0, 1, 0, negative 5, and you get a row of zeros with some other number there. Well, this last one would be 0x plus 0y plus 0z equals 4. That leads to an equation in the form 0 equals 4, which is a contradiction, which means that that system would not have a solution. So just be careful there. We have something that looks like that. And then the other thing to be mindful of is if you have a row that's completely made up of zeros, well, 0 equals 0 is the case that tells us that there are infinitely many solutions. And this is where you have a dependent system. And so you're going to have to solve where you have a variable, like maybe you have z, and then the other two, x and y, are expressed in terms of z. So you would have to go back to the methods that we talked about by hand to at least get it in the format of knowing how x and y relate or how they depend on z. Okay, so that's really all there is here, that you have to be able to convert it to the augmented matrix and then use the calculator to come up with the solution. So let's just make sure you know how to convert it to an augmented matrix. If you have the system 2x plus y plus z is equal to 9, and negative x minus y plus z is equal to 1, and 3x minus y plus z is equal to 9. So what would be the augmented matrix that we would need to enter on the calculator? Or, I mean, you can even do these by hand, but you don't have to do them by hand. Yeah, so our first row is the coefficients 2, 1, right? Remember there's a 1 there. Everywhere we have the variable by itself is understood to have a coefficient of 1 or negative 1. So we really have 2, 1, 1, 9, negative 1, negative 1, 1, 1, 3, negative 1, 1, 9. And you would need to know the size to be able to enter this on the calculator. There are 3 rows by 4 columns. So this is a 3 by 4 matrix. And whenever you enter this on the calculator and perform the reduce row echelon form command, you're going to come up with this 1, 0, 0, 2. Well, your calculator's not going to have the line drawn there. 0, 1, 0, 1, 0, 0, 1, 4. So what does that tell you about the solutions to this system? Right, it would tell us that x plus 0y plus 0z, which is just simply x, is equal to 2. 0x plus y plus 0z, or just y, is equal to 1. 0x plus 0y plus z is equal to 4. So it tells us the solution of the system is a triple 2, 1, 4. Okay? So do you feel pretty good about that? In the homework and in the calculator video, I've shown more examples of how to go through and do this, but really at this point all you need to understand is that to solve a system of 3 equations with 3 unknowns, we can put it in the terms of a matrix and then use the function on the calculator to solve it. So if you have any questions, don't hesitate to contact me. Thanks.